This is Unit 4, Lesson 5. In this unit, we will be graphing complex numbers and then also finding the absolute value of complex numbers. Okay, so first let's start off with the graphing component. So what we're going to do is we're going to be graphing our examples on here, and a coordinate plane was developed where your x-axis represents your real numbers and the y-axis represents your imaginary numbers. All right, so we can use, remember, there's always two values in a complex number. We have our real and our imaginary piece. So for example, we always look at a plus bi. And recall that a is your real number and the b is your imaginary number, okay? So with that being said, when we look at our first example, 3 plus 4i, 3 is the real number. So that's your x value because that's the x-axis. We said our x-axis is our real axis. And the 4, the positive 4, is your y value, right? Because that's our y-axis, our imaginary axis treats as our is the same as our y. So if I want to graph 3 plus 4i, I'm going to treat it like the point 3, 4. Okay, from the origin, I go 3 to the right and I go up 4. And it's this point right here displayed by the pink vector. So when I'm graphing it, I can plot it as a point or I can display it as a vector. Okay. And we're going to use that vector piece later as we're talking about finding the absolute value of a complex number. All right, our second example is 2 minus 3i. That's a complex number. So I'm going to graph it as a point 2 comma negative 3. So once again, remember the real number is your x value and our imaginary piece is our y value because we've transformed our y-axis into our imaginary axis. So 2 negative 3 or 2 minus 3i, 2 to the right down 3, and it's right here, okay, displayed by the blue vector. And then I have the number negative 4 plus 2i, where negative 4 is my real number, and then 2i, the 2 is my imaginary piece, so negative 4 up to over here by the green vector. All right, now do keep in mind, I can write any number as a real or an imaginary number. So with that being said, if I'm just looking at the value 3, okay, we know 3 is a real number. It falls into the real number, integer, whole number, natural, that whole thing, rational, but it's also a complex number. All right, a complex number has a real and imaginary part, so we can write it as 3 plus 0i because there are 0 imaginary pieces. Now, of course, we don't actually write the 0i out, but it is implied because we could write it that way. So when I'm graphing it, I'm graphing 3, 0, and it ends up on the real number axis because it is solely a real number. There is no complex or imaginary piece to it. There's 0 imaginary parts. And likewise, if I have a pure imaginary number, like the example 4i, that can be written as 0 plus 4i because there's 0 real pieces to it. So that when that one ends up getting graphed, it's 0, 4. So it ends up on the imaginary axis because it is a pure imaginary number. So do keep in mind, when I'm graphing a complex number, I need both a real and an imaginary piece. If there isn't a real number to it, it will end up on the y-axis, my imaginary axis. If there isn't an imaginary component to it, like example number 4, it ends up on the x-axis because it's a real number, just a real number. All right, so graphing our numbers. Now the next component is to find the absolute value of the complex number. Okay, so the absolute value of a complex number, for example here, can be written as the absolute value of z once I find it. So it's a non-negative real number, and if you notice, this should look familiar to you, this formula right here. It is your Pythagorean theorem. Okay, because if I'm graphing this point 8 plus 6i, graphing my complex number, I went right 8 and up 6. Well, if I'm finding the absolute value of a number, really we can think of it as the distance from the origin. So it's this blue line right here. And to find the distance from the origin, we can use our Pythagorean theorem, just like you've done a million times before. All right, and even says right here, go ahead and thank your geometry teacher, all right, because the absolute value of a complex number is really the number's distance from the origin in the complex plane. Okay, so if I'm looking at this first example, let's first go ahead and graph 8 plus 6i, 8 to the right, up 6, which is right here. Okay, so I went right 8, up 6 along the imaginary axis, and I want to find the absolute value. So I want to find the distance from the origin. So I'm going to use my Pythagorean theorem. And we know that it's going to be the square root of 8 squared plus 6 squared. Okay, because remember, your Pythagorean theorem is really this, Well, this is the formula. And to solve it, to solve for c, we end up square rooting both sides. So that's why I just kind of jumped right to the square root. It's the square root of a squared plus b squared. Right. So when I go ahead and I do the math, 8 squared plus 6 squared gives me the square root of 100, which is 10. So the absolute value of that complex number is 10. It's the distance from the origin on my complex plane. All right, in my next example, 2 minus 3i, so I'm going right 2, and I'm going down 3 because of the negative, putting it right there, and I want to find the absolute value. So I'm going to do the square root of 2 squared plus a negative 3. Parentheses matter here. Okay, remember, it should be a non-negative real number. So I'm going to get 4 plus 9, which is also the square root of 13. Can't simplify that, 13's prime, so I'm done in that case. Okay, and then in my last one, I have negative 8. So I'm going negative 8, down 15, which actually ends up down there. And then if I want to find the absolute value, distance from the origin, so I had 8, negative 8, and negative 15, which really, when I square them, ends up being a positive anyways. So I have the square root of 64 plus 225, the square root of 289, which is 17. Okay, so that's all we are doing here. All right, and then this is just kind of going through it again. So why don't you go ahead and pause the video. There are 1, 2, 3, 4 examples. I will pause the video as well and go ahead and graph them and find the absolute value. You do the same and then come back and check your answers, okay? So pause the video. Okay, we're back. Let's take a look. So in our first example, we went 4 to the right and then down 5, since it was 4 minus 5i. So then it was the square root of 16 plus 25, or the square root of 41, which cannot be broken down, okay? So it's just the square root of 41. The next one, it was 7i, gave you the wrong part of the axis graph. Sorry about that. It should be the point up here. I gave you 7 over to the right, but still, you can get the idea. Now, for this one, you can just count. If it's on the axis, it's 7 units away from the origin, but of course, we can check it using the Pythagorean theorem. So 0 squared plus 7 squared, blah, blah, blah. It ends up being 7 is the absolute value. All right, in my next two, the first one was negative 2 plus I. So negative 2 to the left, and an I is just one I, so it's up 1. Okay, and I plugged it in and I got the square root of 5, which cannot be simplified. And then my last one, 1 to the right and up 3. So the square root of 1 squared plus 3 squared, the square root of 10. All right, so our summary for today. Remember, complex numbers, any number that can be written in the form a plus bi, where a is the real number, well, b is a real number also, but I is the imaginary unit. And a complex number is a real number a, or a pure imaginary number bi, or the sum of both. So everything is falling into our complex number realm. And then to find the absolute value, we are finding the distance from the origin. And that is all.